features in each of these categories. If you want more information, you can always look through the detailed new features list as part of Start CCM Plus in the downloads, or you can contact your local dedicated support engineer. So the top features and enhancements in version 9.02 for each of these three categories. So let's first take a look at throughput. So we sped up our sliding interface calculation. We've added some new capabilities to the simulation assistant, which we call looping and branching. We also have a brand new overset capability called dynamic overset boundaries, and we've added a new cost function for adjoint, which is the tumble and swirl function. In the realism category, we now have the ability to import native Rhino 3D files. When using volume extraction in 3D CAD, you can now extract from multiple parts, whereas before it was only from a single part. And the directed mesher can now handle baffles, so you can have a source and a target face be coincident. We've included a new deformation model for single-step mesh deformation, and we have the ability to create composite DEM particles out of the CAD shape by filling them with spheres, and we have a new post-processing capability called volume rendering. Now on the accuracy side of things, we have a new capability called dispersed multiphase. We've included the elliptic blending K-epsilon turbulence model. We've also included DAR CFD, so this no longer requires a separate license. We've also included the Maxwell-Stefan diffusion model for species solving, and we also have a new solver for transverse magnetic vector potential. All right, so some things have changed with the 9.02 deployment. So as of 9.02, we are now only supporting 64-bit forms. So previously we supported both 32 and 64-bit, so that's now only 64-bit platforms. We've added some support for operating systems, namely that's Windows 8 and Windows 8 as Windows Server 2012 R2. We've also included on the Linux side of things Red Hat Enterprise Linux 5.5 and 5.8. And at the same time, continued support for Red Hat Enterprise WS 4.3. I want to note that we now require that Java 7 is the version of Java you have installed. So to get the new version of Start to run, you may need to update your Java as well. So because it is in Chinese, so that you have available should you choose to modify your GUI language. We've also changed some Linux installation folder structures to be the same. Whereas previously they were a little bit different due to the starting parallel servers in Windows. One of the features that you may have noticed is for those of you who have power tokens, you can now use power tokens as parallel licenses for all of your simulations, whereas previously they had to be part of Optimate. Use those to spawn jobs on multiple, of course. We've improved our CAD interoperability, and I want to point out those idea storm icons you can see on the left. So the first option, or first improvement I should say, is to import colored STL geometry. So this option allows you to retain the colors of geometry created in CAD and helps you to distinguish your surfaces and also to replace your geometry more easily. We also have the ability to now import Rhino 3D in its native format through our CAD Exchange license. This, of course, gives you better geometric fidelity compared to neutral formats, so you're going to get better CAD straight away. We also have included the ability to import PTC Creo face names, which of course helps in setting up your simulations and having less work for the users. On the CAE integration side, we have another IdeaStorm request that we've implemented in the code, and this is the CAE model import. Now CAE models are imported as regions, and as such, they can be rotated, scaled, translated, or manipulated in a way that other regions created in STAR would be. As such, you can also visualize field functions on these imported regions. We can now import shells and beams. These shell elements and surfaces are imported as shell regions, and beam elements are imported as their own type of beam region. Similarly, we can have bidirectional beam to surface mapping, so you can have file-based coupling between your beams and surfaces for doing things like co-simulation and things of that nature. And on the theme of co-simulation, that is now activated through the physics model selection. So now anytime there's co-simulation from star to star, star to abacus, or star to 1D things like or tools like AIMSIM, OGA, Wave, those sorts of tools, they all get selected through physics model selection. We also now have a user-defined field function available to modify traction in co-simulation with abacus. So you can model things such as hydroplaning, when solid parts come into contact, nullifying the fluid forces. And you can also add a safety factor by increasing the map loads. We've also updated the star to OGA coupling so that we now support OGA 7. Now, one of the biggest changes that may be immediately obvious the first time you open up Magnitude is going to be the user interface. In the GUI, we've made some improvements, notably to the icons, so now they'll look a little bit different. Now, keep in mind, they're still going to have the same actions and functionalities that they did previously, but now it should be a little bit easier to find what you're looking for as we've updated the icons to be a bit more modern style. We also have updated the GUI so that you can use the Shift key for multiple selections, and the count of those objects are now returned. We've modified the measure tool so that you can now rotate your part while using the measure tool. And this overcomes some problems where you may have blocked the second point you need to select by selecting your first point. So now you can move your geometry while using the ruler tool, making it much easier, much more user-friendly. The mesh on-off is also now a single click. This is an idea storm idea. So previously, the mesh on-off was a drop-down toggle. So now we've changed this to be two separate buttons on the toolbar, and we have a single mesh on, mesh off button to make that more user-friendly. And on the theme of user-friendliness, we also want to make it easier for you to find new information or find existing information about problems you may be having with your simulations. In order to do that, we've included links in the help menu to both the Steve portal and to IdeaStorm. So you can navigate to those websites directly. You can also enter in the appropriate keyboard shortcut shown on the screen there to jump straight to those websites as well. Our simulation assistant has two new capabilities, which are branching and looping. The branching capability allows you to modify the workflow based on prior tasks or prior choices. So if you have an option that has, let's say you create a velocity boundary condition, later on in the workflow, then you can only show options which relate to that velocity inlet condition. So the option, this allows you to control the task's visibility based on the selections in previous parts of the workflow. All these tasks are enabled by default, but you can choose to hide them and then show them later on. So these branching workflows allow you to have different workflows depending on the user's choice. And then the looping condition allows you to repeat a task a specific number of times or indefinitely depending on what you're trying to achieve. So let's say you're trying to create multiple boundaries of a certain type. You can set that to loop for however many copies of that boundary you need to create, and it will go ahead and do that for you. There's been a number of improvements to different operations in 3D CAD. So the first of which is the Boolean subtraction. So previously, Boolean subtraction did not allow you to either keep the tool bodies you used or to automatically imprint the tool bodies with the subtracted body that this creates. Previously, that required a number of steps to be done in a specific order. Now you are able to perform all those operations in a single step, which should make this, this sort of operation much more straightforward and much more user-friendly. We've also modified the internal volume extraction to handle multiple volumes, whereas previously all of your bodies had to be united into a single volume in order to use the volume extract. So again, for complicated geometry, this makes the geometry much easier to handle and also simplifies the operations tree. Another part of 3D CAD that we've changed is our Sketch Constraint Manager. So we acquired a new Sketch Constraint Manager to bring us more in line with what you might expect out of a CAD package. So the idea is that we want over-constraining to now be less likely and more easily identified from changing design parameters. And we also want shape distortions to be less likely by changing these different design parameters. Please note that this new constraint manager may impact existing 3D CAD geometry. but any predicted conflicts we've documented, so you can read about those if you think that you may end up having problems with your 3D CAD geometry. We've also included some new tessellation parameters in our 3D CAD geometry in order to try to move problems with excessive refinement or pierce spaces. So there's a new distance-based method designed to fix problems without excessive refinement, with the goal, of course, being to have fewer pierce spaces for the majority of the cases examined. Now, of course, everyone is always concerned about performance, running results faster. And one of the ways we've targeted that in this release is by speeding up the calculation of interface intersection when running in parallel. So we have a speed of somewhere between 3 to 9 times when running in parallel. We've also sped up the remapping of your solution to a new mesh. So if you have an existing mesh with an existing solution and you choose to modify your mesh and remesh, it's going to automatically map your old solution to your new mesh. We've managed to speed that up, in some cases, by over 200 times. So you should see a marked improvement in the time it takes to interpolate your solution from an old mesh to a new mesh in this case. And you can see a chart there for sliding interface calculation times between 802, 804, 806, and 902. So you can see that we've improved that pretty dramatically across a wide number of port counts. Where meshing is concerned, we've made some modifications to the parts-based meshing operations. So when meshing multiple parts, if one of the parts fails, the operation will still continue to completion to mesh the rest of the parts that are applied to that meshing operation. If any of the parts do fail, the user is informed so that they may go back and try to rectify any problems that may have occurred in meshing their parts. So this should save time by not breaking the entire operation, so that if a single part fails out of 10, the 9 parts are meshed, and then the one that was a problem can be modified and remeshed successfully. This is also available for the surface wrapper, which will behave in the same way now. For directed meshing, we've exposed the properties of the directed mesher in the simulation tree, so now you can modify those settings without having to enter the directed mesher edit mode. We also now support baffles, so that you can have a source and a target be coincident and form a loop. This is required for things like loop end windings, if you happen to be dealing with motors or things of that nature. We also have a new motion capability. This is to do with our overset, where we have a piston motion type. And this allows you to set up the motion of a topological piston where the mesh behind the piston is deactivated. So in this case, we're showing a tooth, in this case, being pressed over a post with some glue in the middle. So you can see that we have 2 overset regions here, and we have the mesh being deactivated behind the piston in this case. This goes along with a new dynamic wall overset boundary. So in this case, you'll note that there is no background region between these, around these meshes. So we have the wall boundary on the outside here is dynamically changing between being a wall on this outside, and between these 2 regions is changing to that of overset type. So in this case, we do not need a background region in order to have these 2 dynamic overset regions. We've also modified our DFBI model properties. So now you can set your body properties in an arbitrary coordinate system. So previously you had to set the body properties in the lab coordinate system. But in order to make things much easier and much less time consuming for the user, you can now, let's say, put a coordinate system on your DFBI body and then set the body properties in that new coordinate system, which makes much more intuitive sense because you don't have to handle the translation or rotation from the lab coordinate system. We've made some modifications to our virtual disk model. So the first change we've made is to the blade element method applicable to helicopters. We now have an option to specify and account for the blade sweep. And you can also apply a tip correction to account for lift degradation due to the tip effects. For the body force propeller method, which generally applies to marine propellers, we've included new reports to track the evolution of advance ratio and rotation rate. And you can also set the propeller-handedness, whether it's left or right-handed. There's also a new wind turbine method. So this is a new virtual disk method specifically designed for wind turbines and wind farm modeling. So if you're doing large-scale site modeling with wind turbines, this would be an excellent model to use. And for those of you doing multi-phase simulations, making use of Eulerian multi-phase. We now have modified our lift force model to include a lift correction option to account for multi-particle effects. So previously, where you had drag correction, for multi-particle effects, you would include lift. The lift also simultaneously needs to be corrected, so that's now included. And this improves the numerical stability, always a good thing in these multi-phase simulations. We've also combined both explicit and implicit under-relaxation for both volume fraction and SCAN equations. So generally, the implicit under-relaxation tends to act locally, slowing the solution propagation, and the explicit under-relaxation tends to act more globally to damp solution change. And you can use these together to possibly reduce the overall solution time. So on the right, you can see a graph where we have the implicit and explicit under-relaxation factor swapped for a multi-phase degassing case in this case. So you can see that by specifying a higher implicit under-relaxation factor and a lower explicit under-relaxation factor, we can get convergence much sooner than doing it the other way around. So this is one way to possibly speed up your multi-phase simulations. On the other side of multi-phase, we can look at Lagrangian. There's now the ability to specify the Lagrangian particle injection via a table. So the picture down at right was specified particle velocity and location via a table injector. We also have the ability to specify depletion criteria for cases with particle mass transfer. And the idea is that we want to reduce simulation time by removing small negligible particles. So you can choose to remove particles based on diameter, mass, time step, or some user-defined field function. And this applies to all the Lagrangian mass transfer models. So this should help you speed up your simulations by getting rid of negligibly small particles. You can also now show partial time step as a field function, so you can use that in your simulations as you see fit. And we've also renamed the Haugen erosion model to the DNV model, simply because that's more of what it's commonly known as in the industry. So it's still the exact same model. We've just named it to bring it more in line with the industry standards. In DEN, the discrete element method, we've made some performance improvements using the option to reorder the DEN particles every n number of iterations. And by doing this, we've seen speedups of up to 30% in some cases. There's a very handy, again, idea storm suggestion that we've implemented, and this is to create composite particles from CAD parts. So previously, if you wanted to create a composite DEN particle, you would have to manually specify the location of each sphere in space and its diameter. Now there's the ability to use a imported CAD part and specify the total number of spheres and have the code automatically fill that CAD part with the user-defined number of spheres. So the user has control over the level of resolution by specifying either more or fewer spheres to make up this DEN CAD part. And again, on DEN composites, we can also now distribute the parallel bond strength. So previously, parallel bond strengths were fixed constant across all DEN bonded particles. And now there's an option to randomly distribute these parallel bond strengths based on either a uniform or a normal distribution. There's also a damping model mirroring the surface contact models. We have a brand new multi-phase solver, which we call the dispersed multi-phase. This is designed to be a new lightweight Eulerian multi-phase model, used to model very small droplets, such as water or rain droplets in the air. Generally, the DNP phase is used to feed the fluid fin model, and this gives you improved impingement distribution and is significantly faster than the Lagrangian approach. So the way this works is the DNP phase are superimposed on the primary flow solution and are coupled one way. So the DNP phase knows about the primary flow, but not the other way around. This has two main advantages in that this approach is generally much faster than Lagrangian, and also avoids the patchy impingement that the ground gene usually has unless using an extremely high number of particles. So this is great for vehicle soiling applications or icing applications in this case. And speaking of icing applications, we've also changed the way our mesh morphs in icing applications. So the density of the removed solidified mass of the ice may differ from that of the film, which is usually water. So previously it was assumed that the ice was the same density as the liquid film, but this is of course not the case, and is particularly important for modeling lime ice buildup. So in this case, you can specify the density of the ice separately from that of the liquid film and simulate more accurate ice buildup. Now, the buildup of ice is also a very slow process, and it comes at a time scale many orders of magnitude slower than that of the fluid. So in order to combat this, we've included an accelerated scaling factor in STAR CCM Plus so that you can accelerate the ice buildup and mesh morphing without affecting the flow field, so you can achieve the same ice buildup result much more quickly and much more efficiently. We've included a new turbulence model. This is the elliptic blending K-epsilon turbulence model. This is an entirely new best-in-class four-equation turbulence model. So this is closely related to the V2F model, as it's a four-equation turbulence model, but it's designed to be much more robust. So generally, the V2F model is designed to accurately model near-wall flow that has robustness issues, so it's not always practical choice. So this elliptic blending model has the same benefits, but it's far more stable. So this accurately models near-wall anisotropy, despite being a relatively cheap eddy viscosity model, and it's valid in both the low Reynolds number boundary layer and also the high Reynolds number bulk flow. So the example here you can see is a wingtip vortex, which dissipates prematurely with RKE2 layer, but is well predicted by the elliptic blending. We now have the capability to also do radiation with solid shells, providing support for semi-transparent solid shells. So previously this was only available with opaque shells, but now you can have semi-transparent shells so you can model things like headlamps or windows. You can also now do radiation with multi-part objects, so you can use the S2S model with multi-part boundaries, and these radiation inputs are then specified per boundary. In this case, we're looking at an electronics cooling example. This is also important for vehicle thermal management simulations. Where our species solver is concerned, we've now included the Maxwell-Stefan diffusion model, which is a new multi-component diffusion model more accurate than Fick's law. So you can see some examples here where that might be applicable. We also have some new models for reacting flow. We've specifically included a new micro-mixing model for liquid-liquid reactions. This is important for applications like stirred tank reactors, where mixing due to turbulence is important. This is an eddy contact model, which accounts for those turbulence effects. We also have a turbulent flame speed closure model. This is very important for modeling the propagation of turbulent flame fronts. And in these cases, the turbulence controls the mixing of the flame front, which determines the speed of propagation. And there are three options for this at the moment. There are the Zemont, Peters, and of course you can write your own user-defined model as well. And now there's a new partially stirred reactor model. And this is designed to be used as a test bed for complex chemistry mechanisms before more expensive full simulations. So this is designed as an inexpensive tool to pre-test RCFD models with detailed chemistry before running a full simulation, which would be very expensive. We also have some further improvements on reacting flow. This is the identical mixture fraction space option. So this reduces time to construct this, the PPDF table. So generally the table contains statistical representations of each species in reaction, which would be too expensive to calculate directly. So certain parts of this matrix have a relatively small effect and can arguably be neglected with only a small effect on accuracy. So this reduces both the size of the table and the time to construct it, and also allows the simulation to run faster by reducing the time per time step while the simulation is running. This is available for both the PPDF equilibrium table and the PPDF ringlet table. And one important thing to note is that StarCFD no longer requires a separate license. This is now included for free with StarCCM Plus. And post-processing, you now have the ability to visualize both the forward and backward reaction rates, so you can understand better what's happening with your reactions in your simulation. Our flow solvers now have the capability to blend first and second order differencing, so you can choose to have higher than first order accuracy, but lower than second order accuracy if that proves difficult to converge. So you could choose perhaps 1.75 order in the solver, and that's going to blend first and second order stencils together to solve your simulation. We also have now unsteady preconditioning for the coupled solver. So the preconditioning is used to allow the coupled solver to solve low-speed flows, as it's inherently a high-speed compressible solver. So generally, this is only available for steady-state simulations. This is now available for unsteady simulations and improves the unsteady solution performance. It improves the performance and the convergence per time step in this case. We also have unsteady flux dissipation corrections. So this is important for acoustic simulations using trim meshes, where previously there was an issue where spurious sound waves could be reflected at a mesh size transition. So this enhancement reduces those spurious reflections by dissipating limiting based on the local acoustic CFL number. We changed the options on some of our boundaries, so we now have an option for reverse flow direction on pressure outlets, and those options are extrapolated from interior, normal to boundary, or in components or angles in your absolute or relative reference frames. And these can aid convergence by specifying a more realistic value. So in some cases where you have swirling outflow, an inlet absolute normal is likely to be cause of convergent issues or divergence. So this will give you much more stable and accurate simulations in this case. Our edge joint has a new tumble and swirl cost function, and this is designed specifically to address the needs of powertrain users. So this is important for steady-state port flows in internal combustion engines, and it's available as a report, which is also available to be used outside of edge joint if so required. Now all cost functions are now tied to reports, so this includes the tumble and swirl, pressure drop, and uniformity deviation reports. And perhaps the most important or relevant one here is the pressure drop report is a new report available outside of edge joint, which is a highly requested report by many, many users. So now, to calculate the pressure drop between, say, an inlet and outlet, you can now use a single report specifically designed for that, instead of having to create multiple reports and an expression to subtract the two. This can be done automatically in a single report, saving you, of course, time and effort. And we also have included a new mesh deformation model, so you can morph the geometry in a single step. And this gives you the ability to much more robustly change the mesh in a single step and improves the study of design changes for moving bodies or morphing bodies if you want to change your geometry. We have some additional turbulence model options added to the harmonic balance solver. So there's the standard KEpsilon turbulence model, including the two-layer standard KEpsilon. We've also included the V2F KEpsilon and the AKN KEpsilon model. There's improved parallel scalability. We've improved parallel scalability up to 3 times over version 806. So now if you're running harmonic balance simulations, they should scale much more linearly across highly parallel environments. Another highly requested improvement for post-processing is the ability to use part surfaces for arbitrary sections and probes. So previously you would have to take a part, export it, and then re-import it as an arbitrary surface. And now you can do that directly from within the software. There's no need anymore to export and re-import parts to create arbitrary surfaces. You can also create force and moment reports now using boundary thresholds. So previously, this reporting was only available for regions and parts. Now you can apply thresholding to obtain loading plots. So in this case, you could do something like combine with JavaScripting to automate the creation of lift and drag plots along the wing. We have a brand new capability in post-processing called volume rendering. This is a new scientific visualization technique, and we want to use it to go beyond isosurfaces and actually look at functional variations within the volume of your data. So volume rendering density changes gives you a direct way to visualize gradients. So for in this case, you may have more opaque regions indicating sharper gradients in this case. So in this illustration, we're looking at a static mixer showing volume fractions on derived planes on the left. And while we get a sense of the mixing along the axis, the volume render visualization at right gives us a much better idea of what's going on in this mixer. So we can see how the material is getting split into lamellar sheets as it passes through these mixing elements. So I think it would be very difficult to figure out what's going on the right if we were only looking at what's going on the left. And to make volume rendering practical, we've included a new feature that is the ability to resample a volume. So you get complete control over how coarse or dense you want to make your visualization, and this resampling is also adaptive. So if there's volume refinement at the surfaces where gradients are likely to be high, and coarser resampling further away where the gradients are likely to be low. And I'll be giving a quick demo of this after I go through the new features presentation so you can see exactly how this works and may apply to some of your simulations. We've changed the way that Star CCM Plus works with Optimate and Optimate Plus, so we've improved the licensing structure and that it behaves as other Star CCM Plus add-ons, and that each design campaign requires a Star CCM Plus session license from start to end. And there's a new option to preferentially use Star HPC licenses instead of polytokens for these parallel cores. We've also extended our design and experiment capabilities, so you can now do both 2 and 3 level full factorial design and experiments, and you can also input a response surface to use that for design and experiment analysis. We have also improved our stochastic analysis so that you can include constraints for failure analysis studies if that's something of interest. StarCast has had some pretty marked improvements, namely that it has adaptive time stepping. So this is an entirely automatic process based on the Courant number in each phase. And we've written an algorithm which automatically adjusts your time step with respect to mass conservation and also capturing the stationary behavior of the free surface. This results in a considerable savings on turnaround time for those using StarCast. So for example, what took 36 hours in version 8.02 now only takes 16 in version 9.02 on StarCast. And continuing with StarCast, looking at the user interface, we now have new physics to simulate more sophisticated and realistic effects. So these are the inclusion of oxide films and also macro porosity. We've now included some latest best practice for robust and time-efficient simulations. This is density limiting for ideal gases, free surface interface momentum dissipation, where you have extremely viscous fluids in contact with fluids with very low viscosity, and artificial compressibility. For battery simulation module, we have the enhancement of the equivalent circuit model formulation, the RCR table, and also the NTGP table models. This new formulation is moving away from polynomial fitting to prefer a table formulation, and interpolation between these values as a function of state of charge is done using B-splines. This linear interpolation is used to compute values at intermediate temperatures. Charge and discharge rate is accounted for in these RCR table models, which improves accuracy prediction at high rates. We've also improved the mapping between the electrochemical and the CFD solvers. If you're interested, you can also link the system design, link to the system design software AIMSIM for even further exploration of your simulation or process. Now to talk about the speed, we've improved the motor tool import wizard, so we now have full support of single tooth landings from the coil side model, and that's a new feature in Speed 902. We also have the direct creation of rotor field bindings and automatic identification of the sector model, which simplifies the model setup. Where electromagnetism is concerned, we've included a new transverse magnetic vector potential solver. This is a 2D solver. This is a transient mode which facilitates the resistance limited eddy current modeling. So you can study things like permanent magnet losses or proximity effects in your electrical systems. You can also record back EMF. This has been simplified for both 2D and 3D excitation coils. So this facilitates coupling field and current circuit simulation with the battery sim model circuit solver or other network solvers. We've also improved the BSM circuit solver reporting, looking at voltage drop per circuit element in this case. And finally, we've of course added all of this to our documentation. We've improved and included some new tutorials, bringing us up to 94 total tutorials. And the new tutorials that we've included are in the marine category and open water propeller. We've also included a tutorial on the dispersed multiphase, looking at airfoil icing. We've included a StarCast tutorial for investment casting. And we've also included an aeroacoustic signal post-processing, looking at FST and wave number. We've also added to our verification suite cases. So now we are up to 63 cases with 101 tests, which verify our flow and energy solvers, our turbulence, and this is in this case 2 variants for each of the 4 new cases, and also a variant multiphase turbulence. So with that, I'm going to go ahead and close my presentation, and let's take a look at a quick demo of volume rendering. So let me go ahead and open up CCM Plus, and let's take a look at what version 9 looks like. And let's talk about how this volume rendering works. So while I'm loading, I want to point out, so I want to talk about the previously available post-processing capabilities, and then what volume rendering gives us. So to show our geometry here, what I have is a simple box, and I have a simple pipe in this box. So I'm going to be looking at flow past the pipe. So I have an inlet on this side here, and an outlet, of course, on the other side. And we're just going to be looking at steady-state flow over this pipe. So I've already run the simulation. And let's take a look at some of the post-processing we have available if we want to interrogate what's going on in this flow field. So of course, the easiest thing I could do is to show a plane section through my domain. So in this case, I'm looking at turbulent kinetic energy. And you can see in a single section of geometry what this turbulent kinetic energy looks like. And that's great if I want to know what's happening in exactly this location, but it doesn't really tell me what's going on elsewhere. So in that case, maybe I want to create an isosurface. So if I create an isosurface, again, turbulent kinetic energy, this is going to show me where my turbulent kinetic energy, of course, is some fixed value that I've specified. Again, this shows me lots of information, but it only shows me one specific value. What if I want to know what are the values next to this isosurface? That's where volume rendering really comes into its own. So this is what volume rendering looks like in this case. Again, this is looking at turbulent kinetic energy. So the way volume rendering works is we are showing actually a scalar value in our entire domain, and then we're changing the local opacity based on the local value. So you'll note that my color bar in this case is from some low value to high value. And I have my color bar set up so that high values are opaque and low values are see-through. So although we're technically showing what's going on in the rest of the domain, the value is low enough that that part of my domain has become entirely see-through, and I can see the area of interest in this case. So I can see that the values of high turbulent kinetic energy are completely opaque, and the values that are somewhere in between are partially opaque or translucent. So it gives me a lot of insight into what's going on in my flow, and shows you what's going on not only in a single location or a single value, but shows your entire volume at the same time. So let's take a look at how to create a scene like this. So the first thing I'm going to want to do is come to my derived parts order. And I'm going to want to right-click and choose New Part, and you'll see we have a new option for resampled volume. So I'm going to click on that. It's going to bring me to a scene that looks something like this. So this is similar to the block creation scene, for example. And you can choose to resize your volume, resample volume, which you wish to use for your volume rendering, so you can choose to only show perhaps part of your geometry if you wish to do that. So you can resize this interactively like you would for any other part of the simulation. And you can also enter in those coordinates manually if you happen to know what those are. Now, the two most important features are these two options here, the cell size to voxel ratio and the minimum voxel size. And you can think of a voxel as kind of a 3D pixel. So your screen, of course, is showing you 2D pixels as you're watching this. And we need to create pixels in 3D. And we're going to use these two fields here to determine how many of those 3D pixels we're going to create. So this is going to determine how small they can get, and this is going to give a ratio, of course, between cell size and voxels. So if I go ahead and click Preview, it's going to tell me approximately how many, or well, exactly how many voxels I'm going to create with my current settings. If I change my cell size to voxel ratio, so maybe I change this from 0.1 to 0.01, and click Preview again, you see that my voxel count has decreased in this case. And I get kind of a preview here showing me how these voxels are distributed. I could do the same thing to change my minimum voxel size. Maybe I want this to be a bit bigger, and we'll see how that changes my volume render as well. So once you're happy with the total number of voxels you have, and I personally would recommend somewhere from 1 to 6 million. More than that doesn't really give any increase in quality. It just makes it harder on your graphics card. So let's go with something, in this case, maybe I'll go with something in the neighborhood of my 2.9 million, sure. And I can choose to create either a no displayer, a new scalar displayer, or an existing displayer. So in this case, I'm going to choose no displayer because I'm going to create a scene separately in this case. So I'll choose no displayer and click Create. And once that's done, I can click Close. And if we expand our derived parts folder, you'll see this is the resampled volume that I just created as my new derived part. So now I can use this in a scene that I create later on. So let's say I want to create a new scalar scene. So I can create a new blank scalar scene like I'm sure we've all done many times. So if I go ahead and drag and drop this new resampled volume into my scalar scene and add it to my scalar 1, we've now added that resampled volume to our scalar. So if we go to our Scene Plot tab and expand our scalar, we'll see that's been added to the parts folder. Now like any scalar, we now have to decide what we're going to show. So in this case, I'm going to choose a scalar field here, and let's say I choose the same one, so I'll choose, let's say, turbulent kinetic energy in this case. So if I scroll down in my list to turbulent kinetic energy, it's going to show me, in this case, it's going to show me a blue block. And this is because I need to change my color bar settings. So if I come to my color bar here, you'll see the default color map is blue-red. And if you expand these options, you'll see we have a couple more options, specifically the blue-red band, high pass, and low pass. So those of you familiar with filters will note that this is a band pass, a high pass, and a low pass filter. So if I want to see the high values and filter out all of the low values of turbulent kinetic energy, let's choose this one. So this is the blue-red high pass. So what this is going to do is it's going to say, I want the high values of my scale to be opaque and the low values to be completely transparent. So that is how you would add a new resampled volume to a scalar scene and show a scalar field function on it and visualize your data. So with that, I'd like to go ahead and conclude my presentation, and let me go ahead and take a look at the chat to see what questions have come up. So it looks like my slides have been frozen. Are those still stuck for everyone, or did those update? Can someone raise their hand and let me know? Can you see everything? Okay, fantastic. I have a question. Is adaptive time stepping available in other modules besides StarCast? Unfortunately, no, not at this time. Adaptive time stepping is only available in StarCast. But we have been talking with